Hi, I'm pleased to be able to record this talk about ground-based synergies and connections with LSST. This was prepared by David Alonso and myself, but really the talk represents a large group of people who are interested both in LSST and Rubin science and who are working in ground-based CMB cosmology and experiments. And you can see from the first slide that a lot of the work that's been going on from the ground in CMB science has been done either from the South Pole, as you can see on the right, and then also has been done from the Atacama Desert. Both sites are very dry, and that of course is, and very high, and that makes it really excellent places to do CMB cosmology from. So this time scale, which is shown by, made by Julian Borrell, provides a nice insight into what is happening in the next decades in terms of CMB cosmology from the ground. So it's actually a really, really exciting time for ground-based CMB science. And from right about now, we actually have a lot of different groups that are under operation. So historically, the Atacama Cosmology Telescope and the South Pole Telescope and BICEP and Keck, they have been operating already and will continue to do so. But as we prepare for the next decade, all these experiments are ramping up in both a number of detectors, building new telescopes, so that we can continue to do cutting edge science from the ground, CMB science from the ground. So, as I said, the Atacama Cosmology Telescope, ACT Pole, its polarization sensitive detectors, is currently taking data and under operation. And in fact, we just released our fourth data release as of a couple of weeks ago, which gives to the community a lot of maps that we've been making over the past while, and we have a lot more maps ongoing. We're operating from Cherotoko in the Atacama Desert, a very high and dry site, and the Large Aperture Telescope is mainly what we have at that site. This is currently already being ramped up and developed into the Simons Observatory, which is a collaboration between the Simons Array, which is also on the site. Sorry, I should have actually said that before. The Simons Array and Polar Bear is on the same site, and we're ramping up together to form the Simons Observatory. So this is a next generation instrument that will go from roughly 10-ish thousand detectors to more like 30,000 detectors in both the small aperture telescope and the large aperture telescope. The key thing is that we want to measure both large scale modes, so you need the small aperture telescope to go really deep on smaller patches of the sky with incredible sensitivity. And then you want a large aperture telescope so that you have fine resolution to do a lot of cross-correlation studies and understand the small scale anisotropies. The Simons Observatory will be operation from around 2022 and will continue nominally for 5 years, although we have plans to extend as well. This will then combine the South Pole Observatory with the South Pole Observatory and will form CMB Stage 4, which will be operational from 2028 to 2033. At least. CMBS4 is a really vibrant community. In fact, there's a meeting ongoing this week as well, planning for the science and the detector technology for the next generation. So this is a very active community. In fact, there is a lot of work ongoing to make sure that we are ready to take all of the successes from the other ground-based experiments and move forward. And this will be a big step up. So you're going from roughly 50,000 detectors to about 500,000 detectors in both to combine the large aperture and small aperture telescopes. And CMB Stage 4 will be a 2-site experiment that will have both operations at the South Pole and the Atacama Desert. Now, why do you care? If you care about optical data from the Rubin Observatory, you care because not only are you learning something from the primordial CMB, you're actually learning a lot about the intervening structure along the line of sight through different observables. So the 3 main things that happen in addition to the primary anisotropies is you measure the lensing of the CMB photons, and these are sensitive to the density of matter along the line of sight in galaxies, etc., and logical structure. You also measure the thermal Sunyaev-Zeldovich effect, which is actually sensitive to the pressure of the electrons in the universe. And so typically that allows us to detect a lot of clusters, but to do more science in addition to that. And then of course, you have the kinetic Synergies effect, which is sensitive to the electron momentum. And so that tells you something about late time objects, about the motions of clusters and gravity, and also tells you something about reionization as well through this electron momentum. So where are we? Well, this is an example from a telescope that both David and I are part of, the Atacama Cosmology Telescope. And we've just released, as of a couple of weeks ago, a lensing map which covers over 2,000 square degrees of the sky. So this is shown in Darvish et al. And you can see here where we've actually overlaid the lensing convergence power spectrum and the CIB map. And you see the visual correlation between these structures, these dusty galaxies, and the lensing signal itself. In addition, we have a large cluster catalog. We have over 2,500 clusters to date, but of course we are releasing this data very soon in a large sample, and that's to be found in Hilton et al. And that's useful because now we have these clusters that are detected through the Synergies effect, but they allow us to really probe and look at these clusters in a wide range of wavelengths and do cluster cosmology. And that, in fact, is one of the first great science synergies between the CMB data and LSST on the Rubin Observatory, is that we'll be able to calibrate the weak lensing mass calibration, use weak lensing to calibrate the mass relation. So the TSZ, you measure the cluster, but of course there's a degeneracy between the cluster mass and other properties in the gas. And weak lensing allows you to calibrate this YM relation, where Y is the signal from the SZ. In addition, we can also find and calibrate high Z optical lensing through CMB halo lensing itself. And so we put out a paper in 2019 where we estimated the error on the neutrino mass, or the sum of the neutrino mass, to be around 27 MeV in a lambda CDM plus neutrino mass cosmology. And that's one of the powerful things if we combine LSST and the Simons Observatory thermal SZ measurements. We also can do external shear calibration through joint analyses of lensing 3-point functions. So kappa kappa, shear lensing, galaxy lensing, and the CMB lensing. And you actually will allow you to, through these combinations of the LSST lensing and the lensing from the CMB, you actually have completely external calibrations. You basically can calibrate the multiplicative calibration factors independently. So the systematics are different, and that allows you to calibrate the measurements and actually brings you pretty close to the LSST requirements of around 0.5%. So it's combining the different data sets with different systematics that allows you to calibrate this relationship. For more details, you can actually see a paper led by Manuel Schahn, who's part of the desk and also an ESO collaborator as well. And this is discussed more in the forecast paper that we put out for the Simons Observatory about a year ago now. There are also possibilities to make really high resolution measurements of thermal SZ and KSZ clusters to really constrain the baryon distribution in the intercluster medium and the intergalactic medium. So we all want to understand just how baryonic effects are come into play in weak lensing observables, and the fact that we have these SZ and KSZ measurements actually allows you another independent cross-check of this. So here you see on the y-axis kind of a parameterization of the star formation feedback, and on the x-axis you have a measure of the non-thermal energy injection. So this will allow you to constrain the pressure profile of these objects through the thermal XZ and KSZ effect. This plot is from Vitali et al. And the forecasts in the Simons Observatory collaboration paper, but you can expect to see some new results coming up pretty shortly understanding some of these in the context of the Atacama Cosmology Telescope measurements. So finally, we can also use the combinations of clustering and CMB lensing to break sample variance. So this was presented in a paper by Mishra Sharma, and again allows you, if you care about things like the growth function or you care about clustering in the universe, then you want to combine different measurements at different redshifts to really probe that as a function of redshift and to really beat down on interesting models also of beyond Einstein models as well. In this case, we're just looking at the error bar as a function of redshift in sigma 8, which is this powerful observable. And again, the combination of the even the baseline forecasts for the Synergies Observatory and LSST Gold allow you to really reduce your error bar quite significantly. FNL is also something that you can open up because of cross correlation. So you have a lot of modes from the galaxy surveys. However, you also have the CMB lensing constraints on clustering, and some of the projections by Morris Mundmeyer suggest that we'll actually be able to get to sigma FNL of around 1, combining both LSST clustering and then either CMB lensing or the KSZ effect from the Synergies Observatory. And of course, this is useful because we know we already have pretty tight constraints from Planck, but some of the interesting models are still elusive, and so that error will allow us to do better on that. This is a table from one of our forecast papers, which shows you some of the constraints we expect from the Synergies Observatory on fundamental parameters, including the tensor to scalar ratio R, but then also some interesting ones for the optical community, the effective relativistic degrees of freedom, the neutrino mass, and also constraints on things like the primordial perturbations at very small scales, like K of around 0.2. So that's actually what I'll close off with. But I'd like to say that one of the things that we are very excited by is to make sure that we have people in the community, both in LSST and in the CMB community, working together, partly because we have very similar science interests, but understanding the systematics between probes is super important because it will allow us to break degeneracies, factor out biases and systematic effects, and bring both the power of the lots of modes that you have in the optical data and the fact that you have different calibration, but also then the wide field CMB data that is also linear and free from some of the systematics that are difficult in optical surveys. So the future is really bright. I hope you have a lot of questions for us and that you join the efforts of both groups to really get involved and think of new science and new correlations that we can do to understand physics with the CMB and optical data. Thanks very much.